Hi folks, welcome to Chael Physics class. I'm John Michael Faconla, a science teacher and YouTube content creator of Chael Faconla. So, now let's talk about physics. Do you ever wonder why a comb attracts small pieces of paper after you run it through dry hair? Do you ever ask why do balloons sticks on your hand or a wall after you rub it? Did you ever investigate why do you get shocked when you touch a metal doorknob after walking across a carpet? Well, if you want to know about this phenomenon, please watch this video until the end. It's no exaggeration to say that electricity both runs modern world and ties it together. From where you sit, you can surely see a machine, a communication tool, or entertainment device that uses electricity. You probably have an assortment of electronic gadgets. Your computer may be the most obvious. Portable electronic devices are everywhere: cell phones, laptops, audio and video player, games and toys. Many electronic systems are less obvious but vital, including those on cars and airplanes in the business and manufacturing. By the end of this video, you should be able to understand the basic properties of electric charge, describe using a diagram charging by rubbing and charging by induction, explain the role of electronic transfer in electrostatic charging by rubbing, and describe experiments to show electrostatic charging by induction. Well, to do that, first let's have an experiment demonstration here. And if I were you, while watching this video, you can try it yourself. You just have to follow the instruction. Alright, let's have this experiment. We have a cloth, a plastic comb, and a piece of paper. First, you have to spread the small pieces of paper on the table. Now, rub a comb. Then, bring the comb near to the pieces of paper. Observe what happens to the pieces of paper. There's another activity that surely you can do it on your own. Charging by rubbing using PhET simulation. We are going to use your Android phone or smartphone. To be able to perform this activity, you have to download PhET simulation application and install it on your phone. As you can see, I've installed the application. And you can see the icon, PHET, PhET. So now, let's get started to our activity. Open the PhET simulation app, installed. Alright, we have here a lot of simulations. We have categories here. We have math, earth science, chemistry, biology, physics. Now for our activity, let's go to physics, electricity, magnets, and circuits. Right, there you can see the balloons and static electricity. Run the simulation, load the simulation, and there you are. So as you can see, we have a jacket, we have balloons. You can change the balloons, 1 or 2. We have the settings there, and we have wall. You can remove the wall or add a wall. 1 and reset. You can also change the settings for the charges. You can show all the charges. You can click the show charges differences, and you can also click the show no charges. Alright, for the activity procedure, rub the balloon on the jacket made of cotton, and we have the question here. What will happen to the electrons on the jacket as you rub it with a balloon? Let's rub it. Alright, what happened to the electrons? Okay, next, move the charged balloon, this is the charged balloon, closer to the wall. Describe what happens to the charges present on the wall. So next, compare and contrast the situation from your observations on the balloon interactions. What happened when two unlike charges interact? What happened when two unlike charges interact? Next, what happens when two similar charges interact? When two similar charges interact. So that's it. For the activity 1, charging by induction, and activity 2, charging by rubbing using FET simulation, we have a guide questions here. Is there a possibility that electrostatic can kill? What is the charge of the jacket as you rub it with a balloon? What is the charge of the balloon as you rub it into the jacket? You can now write your conclusions based on these two activities. The ancient Greeks knew of electric charge. The Greek and the Latin word electrum describe amber, a fossilized resin that becomes charged when rubbed with cloth or fur. Such a charged material exhibits static electricity, so-called, because the charges on the material don't move easily. Early observers noted a slight shock or spark when the charged material was touched. And they also recognized that two charged materials attract or repel on each other. By the 1700s, there were two competing electrical theories. In the single fluid theory advanced by Benjamin Franklin, the electrical forces results from the excess or deficiency of an electrical fluid that flows from one matter to another. Materials then attract or repel based on the fluid's tendency to equalize. Two objects with an excess and deficiency are attracted to one another, while a plus is repelled by a plus and a minus by a minus, so to avoid the further imbalance. This theory is not correct, but we've retained the plus and minus designations. The competing theory, which eventually proved more accurate, was advanced by the French physicist Charles and his colleagues. This theory holds that there are two distinct kinds of electrical charge, with like charges repelling and opposites attracting. In England, Stephen Gray distinguished two types of materials: conductors, which carry electricity effectively, and insulators, which do not. Most materials fall into these categories. Two other categories emerged one recently. Semiconductors, the heart of modern electronics, conduct electricity much better than insulators, but not as well as conductors. Superconductors are materials that become perfect conductors at low temperatures. Electric charge is everywhere, but it is usually not obvious. That's because atoms contain equal amounts of positive and negative charge, so they are electrically neutral. The positive charge resides on protons in the atomic nucleus. The protons attract an equal number of negative electrons, which swarm around the nucleus to complete the neutral atom. In 1913, Niels Bohr presented a model of atom much like a miniature solar system, with the nucleus as the sun and the lighter electrons orbiting like planets. As you learn in next video, the force between protons and electrons has the same 1 over radius squared distance dependence as in Newton's law of gravitation. So electrons in Bohr model describe orbits similar to those of the planets. Although Bohr's model has been superseded by quantum mechanics, it's reasonable first step in describing atoms. Because electrons are so light, they're highly mobile. An atom can lose one or more electrons to become a positive ion, or it can gain one or more electrons to become negative ion. This picture shows how attraction binds oppositely charged ions to form crystals of table salts. The attractive force between opposite charges binds all molecules, not just ionic ones like NaCl or sodium chloride. Molecular bonds ultimately results from the arrangement of positive and negative charges in neighboring atoms. That's true not only of individual atoms but also of solids, where the electrical attraction between neighboring atoms gives the solid its structure. When you stand on the floor, electrical forces from atoms in the floor support you and keep the floor from collapsing. Observe carefully and you'll see that the uncharged small pieces of paper is attracted to a charged cone before any charge transfer takes place. The reason is charge polarization. Although individual charges in the insulating small pieces of paper are stuck within neutral molecules, those molecules become polarized by the presence of the charged cone having more negative charge on one side and a compensating positive charge on the other. They act as electric dipoles that aren't free to move but can change orientation. When the negative charge cone is broadly nearby, the positive portion of the dipole is closer to the small pieces of paper. The net effect of the negative cone on all the dipoles is a weak attraction. Polarized molecules still have zero net charge, but the charge isn't distributed uniformly. Charge polarization is a common phenomenon. Run a comb through dry hair and you'll find it attracts small pieces of paper. Break a chunk of styrofoam and it beats clean annoyingly to you. Rub a balloon to give an excess charge and it sticks to your hand or a wall. In these examples, the paper, the wall, and you and your clothes all become polarized and attract charged object. A polarized molecule that you use every day is water, which is sometimes called the universal solvent. Its chemical structure makes water molecule a permanent electric dipole, with the hydrogen slightly positive and the oxygen negative. The molecular dipoles attract ions and in an ionic solid such as sugar, which helps dissolve the solid. You frequently acquire excess charge, especially in dry weather. The classic case is walking across carpet. Your shoes pick up electrons from the insulating carpet, and if you remain insulated, there's nowhere for this charge to go. Because no insulator is perfect, the charge will slowly drain off. But if you touch a metal doorknob, a conductor, much of the excess charge flows quickly into the neutral conductor and you feel a shock. It's a lot harder to retain charge when the air is humid. Water isn't an excellent conductor, but it's good enough to draw away excess charge. The weak conducting properties of water also make it dangerous to handle any electrical equipment when you're wet. The shock you get from static discharge may be uncomfortable, but it's usually not dangerous. However, some situations require care. You may acquire a charge when sliding across the seat as you get out of your car. Then you'll get a shock when you touch the metal of the car. If you're filling your gas and discharge yourself around the pump nozzle, the spark can ignite the gasoline. Hence, warning shown. Grounding, literally connecting conductors to the earth. This grounding, can reduce the risk from electric discharge. Tanker trucks carrying flammable fuels sometimes drag a chain, which keeps the truck grounded. Before fueling an airplane, the fuel technician connects a wire between the plane and the fuel tank to prevent an electric spark. When you fill a metal gas can at the gas station, you should put the can on the ground, never in the back of your car, so it remains firmly grounded. Technicians working on computers ground themselves to prevent static discharge from damaging sensitive electronic components. Let's talk about charge units, conservation, and quantization. Electric charge is a distinct physical quantity, like length, mass, and time. The SI unit of charge is a coulomb, named for the French physicist Charles Augustin de Coulomb, who discovered the Force law for electric charges. However, it's also convenient to think the coulomb is being about 6.25 times 10 to the power of 18 elementary charges, where the elementary charge E is magnitude of the charge on the electron, and the proton is equal to 1.602 times 10 to the power of negative 9 coulomb. It's remarkable that the proton and neutron, although very different in mass, carry charges of exactly the same magnitude. Positive E for the proton and negative E for the electron. Notice that the proton and neutron have nearly the same mass, but the electron is much lighter. In a 1911 experiment, Robert Millikan first measured the electron charge and determined that charge is quantized, coming in discrete multiples of the elementary charge. Today, we know now that there are smaller units of charge, carried in the quarks that make up protons, neutrons, and many other particles. Experiment shows that charge is conserved quantity. That is, net charge, the algebraic sum of all charges including their sign, positive or negative, within closed system remains constant. You can move charge around and transfer it from one body to another, as in charging by conduction, but the net charge in any closed system doesn't change. To sum up the video lesson, here are some points of what are we really talking about. Just take note of it.
Before we say goodbye and end this video, you can check what you've learned on your own. Just try this question.
A suspended object A is attracted to a neutral wall. It's also attracted to a positively charged object B. Which of the following is true about object A? A. It is uncharged. B. It has a negative charge. C. It has a positive charge. Or D. It may be either charged or uncharged.
To deepen your understanding, please take this home.
Well, that's all for today. Thank you for watching.